Thank you for a fascinating lecture. After listening to you, I know why I cannot be a mathematician. But anyway, it seems that a lot of your inspiration actually some of it comes from some old literature, like from Fisher or from Shep, etc.
Sure.
So what is the process whereby you rediscover the gem in the old literature?
About good luck. I don't know. I think it argues, and more than just a broad computer science and statistics and mathematics education, this requires being able to fathom what the biologists are doing, why they're doing it, what's interesting to them. So it's worse than the question is harder than the one you ask, actually, I think. But when you come to the problem of saying how much is left that you didn't sample, you're pretty sure going to eventually run into R.A. Fisher and I.J. Good and Brad Efron.
Well, Fisher and Good didn't agree with each other.
It doesn't.
In fact, Good made very disparaging comments about Fisher.
But I don't know about this. I think they.
This is Fisher.
This was Fisher originally, but Good poked at it. Yeah. If you recall, meant you didn't know this, and I'm going to tell you.
First met at Los Alamos.
Yes.
And you came and talked to me because of the problem in software debugging.
Yes.
Yeah.
Amazingly, the guy. This was a problem. There were huge codes at Los Alamos. Guys. The weapons division would brag about how long their computer program ran, and I kept saying, I can write one that will run forever. So you only got a few runs, and you were trying to figure out what was going on. Mike McKay did wonderful work with that, but yeah.
And Harry Marks.
Yeah, and Harry, yes.
Yes, Michael. My question is, you mentioned at the end that it's at least a tenfold improvement in computational, yes. And, the problem now is not only that the technology for DNA sequencing is you have that sharp drop of cost and efficiencies, but also the accumulation of the data. So it's more like a community project now. Everybody is trying to do it, and machines flowing around, and newer machines with higher capacity, cheaper, and then people just accumulate the data. So your tenfold of improvement in computational capacity or speed seems to be negligible, almost. What do you think?
So I think the tenfold, I was really aiming at the machines that were reading the sequence, like the Illumina machine I showed with all the spots on it. So it's there. That's the critical. At least that's my eyes on that part. So that's what the cost, the raw cost of getting the data to give you a human genome. Of course, you have to actually decipher that data, which is another issue. But yeah, I'm not talking about computer speed. I'm talking about speed of the sequencing machines. How's that?
What about computer speed?
Well, I know even less about that.
Professor Yang? Yes, thank you for a very interesting lecture. And you mentioned briefly about the issue of complexity. When you do the PCR amplification library, there's asymmetric amplification, and so you mentioned there's some algorithm that can fish out those less abundant sequences. Now, in the biological system, this sort of issues happen all the time. For example, if you're looking at the cancer, for example, there may be some cancer cells or cancer DNA circulating around the bloodstream. Yeah. So probably one molecule out of 1 million.
Yeah.
Now when we perform the deep sequencing, now all these things are mixed up. So is there any way of identify these 1 out of 1 million molecules that may carry some mutations compared to the majority of the sequences?
Yeah, that's an important question for which I don't, once again, don't have an answer. But people spend a lot of time thinking about that now, as you know. But I've got nothing to add to that.
Hey, Michael, you talk about in the overlapping scheme, right? So there are possibilities for errors. Sometimes one symbol is mislabeled, but sometimes it seems to me if you have a missing label, then it's going to throw a whole monkey wrench into the whole equation. Yeah. So when you have, if error is a problem in many cases, is it going to basically make the all-erring graph approach non-robust, or is it still pretty robust?
Yeah, well, if the errors predominate, then that's what you'll get as a red sequence. But if errors are rare, then you can sort of ignore those sort of as a statistician would. But of course, this is all tangled up with all the repeats and so on. This is not simple.
Yeah, please.
Thank you for your fascinating talk. I have a question that some of the new platforms of sequencers may have a cheaper rate of sequencing, but they have a higher error rate.
Yes.
So you have mentioned that if we increase the coverage, then we can compensate partly this error rate. So is there any limit of the error rate, or what is the mathematical relationship that, so for example, if the error rate is 2%, 3%, then we can increase the coverage a bit to overcome that problem. But the error rate increased to 25%, then is there any relationship, mathematical relationship, that we can cover to a certain level that compensates this?
Yeah, so there are some calculations of this in a paper of mine with Gary Churchill on which assumes the assembly's right, and it's trying to do that business of calling the letters from the column. So we can use EM to estimate the error rates of the underlying machine and so on. But of course, you're assuming that you've got things lined up right, and but so there's some calculations in that paper about along the lines like people originally thought that that if the sequence trying to say, they worried about the, if you're trying to say comparing genomes from sequences from two genomes, being confused that if the sequencing error rate was larger than the mutation between the genomes, you couldn't do the inference, and that's just not right.
Yes, is there any theoretical maximum error rate that we can tolerate? For example, if the error rate is 90%, then probably it's unlikely that we can do anything.
I would just go back to my paper with Gary and look carefully at that. But you're obviously right.
Other question and comments? Yeah, please.
Yeah, Mr. Michael Waterman. So I have a related question about the error. So can you think from another angle? So in your sequence alignment or this kind of sequence assembly method, can you report a kind of a possible error bound or uncertainty level to do that? So because current days, when people use this kind of sequence data, we always take for granted. So this is accurate, right?
Yeah. So what Gary and I recommended is that you do, you take the assembly you have, you compute the probabilities that this really is an A and a T and a G and a C and so on, and you would put those in databases, but no one does that. So I think it's a really good idea. The quality of, I think that's the word Phil Green used, quality, which is a word for minus log probability or something like that.
Yeah.
Okay. Any other question? So if not, let's thank Professor Waterman. On behalf of the university, I would just like to thank you with this very small gift. Yeah, thank you.
Thank you very much.
Thank you very much.